So yeah, I think all the presentations are they're very diverse presentation we saw today, from like Kate's really like amazing work about the grid and the place cells. I've been like following that for a long time, and I think is a really brilliant piece of research, to the various works from like Wessam, from Theodore and Saha and Paul. Yeah, so to kick off this discussion, like, yeah, it's like should we go to individual presenters and then asking questions? Would that be a good idea, Abel?
Yes, I think so. Yes.
Okay. So yeah, so do anybody have any questions for Kate? Yeah.
I do, but I can wait because I can give space to the other presenters if they have questions in the audience. But if not, I can go ahead. Okay, I'm just looking here at the chat bar. Okay. Katie, I do have a question, and I have two questions. The first one is what I find really amazing about this type of research is that it seems to be collating a new vocabulary for architecture and how we should be thinking about architecture. The different patterns of firing of cells literally map directly to tectonics, and it seems like it's changing the way we understand architecture. So I would like to open this to everyone to discuss, but is this what you think it is? Is it like a new vocabulary, a new neuroscience based architecture vocabulary that we are creating as we discover new things?
Yeah, I think that's a really good way of putting it. So I think of it as highlighting the role. So, I mean, architecture has often been interested in the emotional components of space, like how people feel when they go into a space. And I think what this work does is also highlight the importance of cognition, so what you know about the space. And it's kind of formalizing that. So we're starting to understand what it is you know about a space and how. And we're sort of realizing certain things are really important, like the sense of direction is my big thing. The sense of direction I've almost never seen discussed in architecture, like how, when you design for people, how will they know which way they're facing when they go into a space? And when you kind of facilitate their movement through a building, how do they update that without getting confused? And if they get confused, how are they then going to make a map of the space and know where things are? And do we care? Is it important? Or all that kind of stuff. So I think for me, it's sort of opening up attention onto things that I'm sure architects knew about but didn't ever really kind of explicitly think were important.
Yes, yeah, I think this is what you're saying is it's very key. We knew about it, but we knew it in a different way. It was a different way of knowing. Was kind of because we have brains. It was kind of guesswork. It was that intuition that thing was happening, but this gives what you've been showing to us, give us a different metric and a very powerful metric. That I think it's incredibly disruptive on how we are thinking about.
Disruptive, that's a good thing, isn't it?
A good thing, a good disruption. We have
just check that our terminology.
Yeah, as in, yeah, we have to rethink our methodologies and how we produce architecture, and I think this is really key.
I actually have a question for Kate. Like from the experiments you showed, the environments were mainly linear, or they were like in either 2D or slightly 3D. Did you run any experiments where the environment was slightly more complex, like in terms of like a plan form, like in a city form? Like were there any experiments of like mice needing to like navigate or choosing between, do they need to turn left or right, or some decision making in this process? Like, were there also difference, yeah, just wondering, like, rather than a flat space, were there any like grid like spaces that yeah, the experiments were ran on, just out of
Yeah, there've been a lot of there's been a lot of work looking. So I mean, that's how psychology started, looking at space and complex sort of mazes, and then we kind of made them simpler and simpler and simpler because we realized that complex mazes are too complex. But now we're sort of starting to build that up again. And one of the things that's been driving that is that we've learned that place cells, they don't just fire in a place, but they also kind of talk to each other. So they will fire in these sequences where one cell will fire, and then the next one, you know, as the rat's walking along, one cell will fire, and then the next one will fire, and then the next one will fire. And these cells become spontaneously active when the rat is dozing or sleeping. And they become active in that same sequence that they did when the rat was walking. So the implication is that they've learned the sequence that was experienced when the rat was awake, and now they're playing it over again in the rat's mind. And so people have looked at what's happening when a rat's at a decision point in a complex maze, and we see the same sequences, one going down one of the possible paths and then going down the other possible path. And it looks very much like the rat is in its mind, sampling, you know, what will happen if I do this, and what will happen if I do that. So it's kind of exploring its mental map, and you can read that dynamically. So yeah, it's all pretty cool stuff.
Yeah, very fascinating. And one a related question is the distance actually really similar between like the grid cells that you have in the brains? Is that distance, like, in terms of scale wise, would they be really distance to like real play, like in the physical world, like the distance between, like, are there any meaning between the distances between the cells?
So do you mean the distances between the places where the cell is active? Yeah. Yeah, that's an important distinction, because a lot of people, when they first encounter grid cells, it's a lot of information to process, and they think that pattern is actual cells in the brain. But it's not. It's the places where one cell is active. And the distances between those places where it's active are quite small if you're recording at the very top of the brain. So maybe like 30 centimeters or something. So and the size of the area where it's active and the size of the area where it's quiet are about the same. So you've got activity, then you've got quiet, then you've got activity, then you've got quiet, and so on and so on. But when you go down deeper in the brain, then the scale gets bigger, up to several meters. But this is all in the head of the rat. It's not tied to the environment scale at all. And also it's not tied to body size. So mice have the same scales as rats do, even though they're really tiny. And baby rats have the same scale that adult rats do.
Okay.
So whatever it is that they're doing, it's not quite as obvious as what you would think when you first encountered them. And we're still trying to work out why, you know, why it's like this, and does the scale mean anything, or is it, and does it mean anything precise? I mean, presumably it means something, or it wouldn't be there. But is it doing a really precise thing, like a Vernier scale, you know, where you've got lots of different scales and then you can do fancy computations? Or is it just the brain wants a few different scales because it's got this very loose idea of size, and, you know, so we don't really know yet.
Thank you.
Oh, hi, Fadil. Yes.
Yeah. Hi. Sorry, I have a quick question to Kate as well, and it's a rather, you know, a geometric question related to sort of the relationship between the circle, the oval, and the hexagonal shape that you had introduced. And so is the hexagonal shape sort of a resultant of a multiple sort of circular activities that are happening? And I guess my other question is if that circle is turned into an oval due to the fact that the space where the rat is, you know, that is experiencing is slightly longer, or it's not a perfect square, does the hexagonal shape a consistent one regardless of that change? And then I guess my other question would be in a three-dimensional sense, where you were sort of categorizing it as a simple extrusion of a cylinder or a spiral staircase. And I was just wondering if these were sort of paths that you were predicting the sort of the rat would register, or were they sort of an outcome of the experiment?
Yeah, okay. So the first question, I think you're referring to the stretchy box experiment,
Right.
where the square was made a rectangle.
That's right.
And is the question about what the rat thinks the scale of the space is, given that the grids have elongated in that dimension?
Right. So it's just simply because I was a bit confused to where the hexagonal shape is the hexagonal shape sort of a resultant of different circular experiences?
Yeah, so the
Yeah.
hexagonal
Yeah.
shape just arises from the fact that, so there'll be a place where the cell fires,
Right.
which is roughly circular.
Right.
And then if you look at all the other places where it fires, which are also circular regions,
Right.
they tend to be arranged around the first one. There tend to be 6 of them.
I see.
And then similarly, if you looked at one of those 6, you would see that around it, there were 6. So
I see.
every
Got it.
field around it has
Mhm.
6 other ones.
Mhm.
So that's just the natural pattern that you get if you try and squash circular things together.
Right.
That's the most efficient pattern that
I
you'll
see.
get with the fewest amount of gaps.
Got
So
it.
that hexagonal pattern is kind of arising from whatever it is in the dynamics of the cells that's making them fire in regions and then not firing, and like having a space around where it doesn't fire, and that's a chance for some other cell to fire there instead. So the question, one of the questions is, does that hexagonal symmetry have any meaning beyond that? Does it have any psychological meaning? So do we have some type of preferential, like, for example, are we better at calculating distances that are at 60-degree intervals?
Right.
Because that's along the lines of some of our grid fields in some spaces and so on. So, might we prefer hexagonal geometries for our cities if we were ever given the chance to experience one, or not? So that's sort of one thing.
Right.
But yeah, in terms of the scale and what happens if you turn the circles into ovals, like you stretch them out.
Mhm.
So we don't know whether the rat, and I presume it does, but we don't quite know how to ask the question, whether the rat has got its distances a bit distorted as well. So it's sort of not sure whether it's in a square or a rectangle anymore, because there's some ambiguous information. So,
Sure.
and then in the three-dimensional stuff, yeah, the extruded cylinders that I showed you. So I showed you a slide of a whole lot of hypothetical things. Were we going to see this? Were we going to see that? And so on. We didn't see the extruded cylinders in a volumetric space. We saw globules. So the grid cells would fire in kind of blobs in the three-dimensional space, but they weren't close packed. So if you packed oranges into a space, into a volumetric space, you'd get a three-dimensional hexagonal close packing. Mm-hmm. But we didn't see that with the grid cells. So it looked like the close packing had broken down. Yeah. And we don't know if that's important. Does it mean that that's because three-dimensional space is not represented as well? It's a bit more confusing. Or is it just a side effect of the way the rat explored and it doesn't have any psychological meaning? So yeah,
the three-dimensionality of it doesn't have a distinct sort of shape like the two-dimensionality aspect of it is.
That's right.
Okay.
Yeah.
Interesting. Yeah. Super interesting. Yeah.
Yeah. And that was true. It's just been published. So we published our paper using rats, and another group published their study of bats, which flew through the space, and they found almost the same thing. Wow. So that seems.
That's super fascinating. Wow.
Seems reliable. Yeah.
Almost unexpected.
Yeah.
Stephen, you're muted. Yeah.
We have a question from Alan to Kate. It seems that there are trace adaptation in rats, pointing there is an interaction between environments and spatial culture. Could Kate elaborate?
Sorry, I missed the first bit of that. There's a.
It seems that there are a trace of adaptation in rats.
Trace of adaptation.
Pointing that there is an interaction between the environments and the spatial culture. Could Kate elaborate?
Yes. So When we first discovered place and grid cells, I think a lot of us thought of what was going on as these cells have this kind of propensity to fire when the rat goes to a place in the environment. So it's almost like there are ghosts of those firing regions out there in the world. And when the rat walks into that space, then the cell becomes active. And so, you know, I guess I think of it as almost like a Platonic ideal of place fields and grid fields, these sort of places. So if that were the case, then, you know, you would imagine that space is permeated by all of these potential, you know, regular places where if the rat goes there, a grid cell will fire. What we've actually found is that the places where the grid cells and the place cells fire depend very much on what type of environment it is, whether it's flat, whether it's volumetric, whether it's horizontal, whether it's vertical, whether it's awkward to climb on, whether it's easy to climb on, like all of this kind of stuff. So it's very much a decision that the cell makes based partly on where the rat is, but also partly on what the rat is doing, like how it's able to move through the space and whether it can move in an unobstructed way or not. So we're sort of now, or at least I am starting to think of the map as what psychologists, cognitive scientists call inactive. I think that's the right terminology. So it's the product of an interaction between your cognition and the world. It's not in your head and it's not out there in the world. It arises from both of those things together. And so it's very individual, like no two animals will have the same map, for example, and no two patterns will be quite the same. So I guess, yeah, adaptive is a very good way of putting it. The map adapts to the particular situation, particular environment that you're in.
I have a question about that, if I may, Kate. I've seen your presentation at UCL on the moths in Australia. Is this a phenomenon that is linked to what you are describing? Because they are born and they fly always to the same place, and then the next generation just fly back to the original place. Is that right?
Yeah, that wasn't my presentation. That was Eric Lund. No, yeah. Eric, I've blocked on his name, from Lund. The bogong moths in Australia migrate and they breed in a place in the Blue Mountains, and then the newly emerged moths can fly back. So even though they've never experienced the place.
Yeah.
Eric Warren. So Warrant. Sorry, I'll get there. It's I'm mixing up two people. So that suggests a hardwired migratory pattern, because the newly emerged moths had never experienced that journey, so they couldn't have learned about it. So there's something genetically encoded about the path, and it may be in the form of a propensity to fly in a particular direction, given the temperature, ambient temperature or something like that. I don't know. I don't think we know what it is. But yeah, there are all sorts of interesting questions. Like those animals are very different from us. So we don't know whether they would even have place and grid cells, or whether that's something that's peculiar to mammals, or is it peculiar to vertebrates more generally? And there's some evidence now that birds certainly have place cells. So it may be vertebrates more generally. But we don't know if invertebrates like insects would have that system, or if they've got something a little bit different.
Is there any evidence that we have any trace of genetic memory in humans?
Of places?
Of places, yeah.
Not to my knowledge. So we do, I mean, I think we do have hardwired a propensity to attend to certain types of information. Like we particularly might notice mountains, for example, or sea. We like water, and we like, you know, rivers and oceans and things like that. So it may be that we have evolved attention to spatially useful cues. But when you think about it, like we've been evolving for millions of years, and in that time the continents have all kind of done a fancy dance and everything's shifted around and sea levels have come and gone and ice is coming. So I don't think we have any genetically encoded memory for specific places, but I think for types of spatial information, we could say that we probably do.
Okay, yeah, that's, I mean, this is so fascinating. It's incredible. I will just, I have one last question for Kate before I talk about Fadil's presentation, if I may. I'm working on a very complex problem at the moment, and this is to engineer a digital twin for a large infrastructure project. And this includes, what we call rolling stock, trains and everything else that runs on the rail. But the scope of this digital twin is quite different from a typical digital twin, which is just replicate, a house in the digital realm or a rail station. We want to, first of all, integrate this to the national digital twin that has been discussed by the CDBB at University of Cambridge, but also enhance all the communities close to that digital twin. So the digital twin becomes a kind of a service layer, if you like, augmenting cognition in the different communities, somehow assisting training, education, data-driven healthcare, etc. And when you present, I was just thinking, if there is a catalog of problems of malfunctioning of natural navigation in humans, and if we have a good understanding of that, because this cognitive service layer could be used to serve neuroatypical people or different types of communities and how they operate. Is there something like that out there? I have no understanding. Maybe it's my lack of understanding of the domain, but I didn't come across.
No, I don't know. This is all very new to me. I've not really encountered the notion of a digital twin. But so is this something that people would explore in VR or something?
Yes, so in reality, I thought it was going to be a VR version of the train, for example, but it's a lot more complex than that. It's about 9 to 10 different databases doing different things and being reconfigured, and it can be seen, can be visualized as a VR or augmented reality element. But it's the idea that you have this constant flow of sensors in the environment informing decisions that need to happen in a number of systems. And one of them, and I'm trying to advocate that, one of them would be data-driven healthcare. And data-driven healthcare in relation to spatial navigation. So the UK has a program for a national digital twin. So every time you create a digital twin, which is the digital ghost of a building or a rail line or something like that, a piece of infrastructure, feeds all this data into a national grid of knowledge, of digital knowledge. But I'm trying to understand and formulate some sort of a strategy that would help people navigate spaces. So that, because there is a huge opportunity, and it is a huge effort, and it's a huge opportunity as well to deploy this digital twin, not only in the asset itself, let's say in the rolling stock or in the railway station, but in the communities surrounding it. So it could be seen from your mobile device. It could be seen from a number of different places.
Right.
So my question is, if there is a kind of a catalog of, I would say, medical conditions of spatial navigation that could be assisted, do we know how to better assist people that would benefit from information to navigate the environment, or is this kind of too abstract?
Yeah, no, I think it's a really interesting question, because I think that this new technology that's coming along is really amazing, and navigation is one of the things we've immediately used it for. We now have maps on our phones, and it's made life so much easier in some ways. Mm-hmm. But one of the problems is that it's it's become too easy to navigate without really knowing where you are. You follow what your phone tells you to do, and you can get from A to B, but you don't really know where anything is. And so one of the things I would like to see happen with this technology in future is that it gives you information that you can use in a map-like way. So, for example, augmented reality, where you look at your phone and it shows you a kind of a glass version of what you can see around you, with your destination highlighted. That may be a couple of blocks away and hidden behind several buildings, but because you're looking through glass, you can see where it is, type of thing.
Yeah.
So augmented reality. So I imagine that could be quite useful for people seeking healthcare. For example, like which pharmacy's got spare COVID vaccines right now, and how do I get there? And you could kind of look on your phone, and it could show you the building, and and show you how to get there, and it could compute the most efficient route, given the several pharmacies in the area that have it, which would be the best one for you, given what else you want to do after that. After that, you wanted to go to the supermarket or something. So you could imagine that it could be really useful.
Could be, yes.
Yeah.
Okay. And then I have a question for Stephen. So absolutely amazing. So it's such a collection of amazing techniques and methods and tools that we've seen in your presentation, in your amazing research. But I was thinking about the feedback loop. When people get to know that certain features represent something, it's an iconography or an artifact of a particular perception of value in that neighborhood, for example. And this also goes to Paul, I think. What do you think about this in terms of a feedback loop? And what do you think about the interpretation of what you are showing in relation to the so-called Griffin paradox? Griffin paradox, as in the perception of value and demand creating supply, or demand or supply generating demand. Sorry, you supply something and then the demand appears. Does this make sense? It's, so when, sorry, yeah. Griffin paradox, as in, for example, in an economical crisis, cheap goods become more expensive. So the price of certain products go up because they are essential. For example, a classic example is the price of bread in an economical crisis tends to go up instead of down.
Yeah, so yeah, thank you for the question, Abel, and also Paul, if you want to jump in, you're very welcome to. So like like I didn't really think about the economic side of things, but I do think the economic environment drives a lot of the process, especially the demands of places, and I do think the kind of criterias are actually dynamic in time, meaning that they do change. So may that be like when you're doing like, and I think as like one of the reason why because usually in traditional kind of like machine learning research, they call human in the loop, where human is part of the machine. But I personally, I see the design process is still very much like the machine is within this human loop process, mainly because I do not think at the moment, a lot of the kind of techniques are very much, you need to set some kind of criterion or objective function, or some kind of like loss or reward, some kind of system to be able to evaluate. But I do think a lot of these things are actually changing over periods of time. So perhaps in certain states within this loop, those kind of criteria actually change. So maybe in some states, and also it also is a complex system as we know cities are. So and I don't think these machines or techniques should be used blindly. It should be used from the perspectives of like domain experts who can interpret these outcomes. So rather than blindly following it, I do think there's a very big space for the humans to basically be able to interpret these results. and they could be different according to the different parts of the loop. And there's always going to be factors that are not going to be modelable or being able to, like, if you try to build an agent-based model of a city, those there's assuming some sort of homogeneity among the agents and all that. So there's always going to be assumptions in the model. You can use it to test as a basis because it's objective. But at the same time, I do think you need to also remove yourself from the kind of, not remove, but like interpret it in the situation within the loop. So it is, I do think it's a more complex process. This is why I always think at this moment in time, the machine is still pretty much embedded into our process of designing rather than being humans being embedded into the machine loop. So I because of the very reasons that these things changes and demand changes but technically some would say if for example, these agents learn from every single data points in every single point in time in history, perhaps they'll come up with the right way of designing. But I think we are still, I think, far from this kind of being able to learn to properly design. So I do think it's more of an assistant more than anything, and I think these things changes. I don't know if I answered your question or if I answered someone another question, but yeah, just a thought.
Yes, indeed. Yeah, it's all very. I just think that once people observe something, then there is an opportunity to remodel value. You know, especially when that becomes visible, like something visible. And say, okay, a nicer neighborhood has more green, and then things change, and very quickly we adapt to that. And then there is a kind of almost like an opportunity to speculate what value means in that particular situation or space. But then there is also this emotional capital that Paul has been talking about. So there's entanglement, entanglement between two things. This idea has been going on in your mind now for a few years, right?
That's right. Yeah, since almost 2018 when grad school had ended, for sure.
Yeah.
Yes.
So this sounds a lot, and maybe I'm biased because I'm dealing with this digital twin kind of challenge, but it sounds a lot levels of digital twin maturity. Mm-hmm. So there are different levels where you have the physical thing and the digital representation of that thing, and they are not connected, so you don't have the cyber-physical link. And this is called level maturity 0, disconnected digital twin. Nevertheless, very, very important. Some people think, oh, a digital twin has to be, an object with a sensor sending information to a database that can be represented in 3 dimensions and can be used to manage some physical asset. But that's not quite true, because when you have this disconnected digital twin, like a 3D model and the 3D printed version of the 3D model, you have an opportunity to do topology optimization, to use, as we've seen today, genetic algorithms, AI, and all sorts of things to optimize things. Mm-hmm. But then there is a growing level of maturity in digital twins that goes from level 0 until level 5. And level 5 is what we call autonomous intelligent digital twins. Mm-hmm. Self-driving cars and autonomous infrastructure projects, which is kind of a science fiction at the moment. We have very few examples in the world. One very good example of a very advanced digital twin is the Hong Kong subway. It's, I think, one of the very close to fully autonomous intelligence. Mm-hmm. But that entanglement seems to be that nexus between the physical and the digital. And I wonder if you see it that way or if you disagree, and what are your points on that?
So the idea that's in my mind, and this still needs a lot of sort of discovery and testing, and a rather practical one. In my head is it's a way of transferring data. So, for example, if it becomes problematic to implement the Internet of Things, if we want to make a smart building, and the only sort of way to do it, at least currently, is to have facial recognitions or cameras or sensors that are measuring things where privacy is being violated, then maybe the sort of data that we can implement into the physical object is actually measured in a different way, implemented into the digital one and relayed into the physical one. You know, it doesn't have to be, it's sort of a reciprocal relationship. And also it has to do with sort of, you know, if there is, not every component in the building needs to be smart, but if there's one distinct component that is smart, it can do a lot of non-architectural work or function. And that in order to update sort of the software through which this component is running, it has to be connected to a digital source. And that digital source constantly feeding information into the physical one and vice versa. So the physical one is collecting data, sort of updating the digital one. And then if there is a new kind of data where we're not able to capture physically, then we sort of do it the other way around, where the digital is informing the physical in the sense of updating the software or becoming more sensitive or becoming, you know, so it's still not 100% sort of defined in my head, but I do think we can draw even parallels between, you know, what does it mean to have an entangled exterior object versus an interior one? You know, what is the exterior one sort of collecting, and what kind of information is it relaying into the interior one? Now, how does that, if that connects back into digital, into the digital aspect of it, then how does that change in terms of the design going forward, right? And if there is a part, like if we're changing the interior component, for example, do we update it with a new sort of updated software? It's like almost changing like the iPhone every time or every year, and etc. So it's mine, you know, sort of the idea that's my mind is rather complex, and it's not just one directional. It's sort of multi-layered and yeah.
I think this is a good moment also maybe to call the day, because we overrun a fair amount and it's getting late. I would like to thank you everyone for the amazing session, really amazing session today. And I listened to every presentation with a lot of interest. I'm very grateful indeed for Professor Kate Jeffrey to make the time to be here today. It's just, in my mind, unbelievably fascinating. And also for Stevens for being here and present the fantastic research he's doing at the Alan Turing Institute, and all the papers who are very insightful and just show how quickly we are changing in this fourth industrial revolution. Okay, so thank you very much, everyone. I will stay on the line, but otherwise I'll see you tomorrow morning. Very grateful, and have a good evening.
Have a good one. Thanks a lot.
Bye.
Bye. Thank you.
Bye.